Good morning, ladies and gentlemen. I feel glad to be present in this conference, Artificial Intelligence and Big Data 2020. So let me introduce myself. My name is Rihab Derouiche. I'm a PhD student at the Faculty of Tunis. Today I'm going to talk about my presentation, cooperative agents-based workflow level distributed data placement strategy for scientific cloud workflows. This work is elaborated by Dr. Zaki Brahmi. In this presentation, I have divided my work into 5 parts. In the first part, I will provide a general introduction where I will account for the general context as well as the motivation in order to identify the problematic. In the second part, related works will be presented. The proposed solution will be detailed in the third part, then experimentation and result, and finally, I will end up with the conclusion and I will give some perspective. Now, let us move on to talk about the first point. Actually, many scientific applications such as astronomy and bioinformatics and big data applications like the smart city existed. These applications are characterized by their intensive computing. According to such statistic, in 2018, the world had 33 zettabytes of digital data, the equivalent of 66 billion terabytes. In fact, in 2020, we have 47 zettabytes of data. This number will be multiplied by a further 3.7 to reach 175 in 2025. In addition, this application needs a high performance computing resource and a massive storage and a massive CPU. Since this application generate and process a massive volume of datasets every day, they are considered as data-intensive workflows. In fact, the automatization of this data-intensive application and the analysis of their data is realized by intensive work. To better identify the problematic, let us consider the example of workflow LEGO, which is a network gravitational wave detectors with observation in Livingston, Los Angeles. It detects gravitational waves predicted by general relativity Einstein theory of gravity. Each workflow executed in pipeline has 60,000 compute tasks, input data 5,000 data, and 60,000 output data. Intensive workflows are considered as complex since they contain a large number of intensive computing tasks in order of 1,000 or 1 million or maybe more. These tasks process and generate a large number of datasets. In fact, when the tasks of intensive workflows are executed, they require for their execution many number of datasets that are physically distributed in different and multiple virtual machines. In fact, data movement will be inevitable and it is considered as a bottleneck since data centers have a limited bandwidth. It appears to be costly in terms of execution time, communication cost, communication energy, and and the global cost of execution of the workflow. It is clear that the emergence of cloud computing ensures the execution of the intensive workflows, improves their throughput and performance, offers a high computing capacity, and a massive storage with a low infrastructure cost. However, the execution of intensive workflows in the cloud computing still face some new challenges, which is the data placement. In fact, ensuring an optimal mapping of massive data used by many scientific workflows to cloud storage service in a reasonable time is considered as a challenging task. Data placement is hence a MP hard problem and its capacity increases with the types of the dataset, intermediate, flexible, and fixed. Data placement has attracted the attention of many researches. In consequence, many approaches have been proposed in this issue. After making an exhaustive state of the art, we have found that most existing data placement strategies focus mainly on reducing the data movement, the time, and the cost during the execution of workflow tasks. However, they neglect the execution time of the data placement process, meaning the optimal data placement in a reasonable time, which is a problem for the real-time application. They don't consider other types of workflow datasets since they are task-level approaches, and also they consider shared dataset within only individual workflows, which is not efficient enough for the situation of multiple workflows. So, to remedy this shortcoming, we propose in this work a cooperative agent-based workflow-level distributed data placement strategy for scientific cloud workflows. This approach consisted in distributing the data placement process across a set of cooperative agents, considering the placement of intermediate datasets generated during the execution of tasks of workflows, the fixed dataset and flexible dataset, considering the workflow level data placement while considering multiple workflows. Our main concern is reducing the execution time of the data placement process, the data placement, and the communication energy consumption. Approach is based on the formal concept analysis. So we turn on to define the mathematical foundation of this approach. So we start by the formal context, which is a triple R, O, I, O, A, and I. For the first set is the set of objects, which are tasks in our case. I is the set of data, or the set of attributes, which is the set of data in our case, and I is a binary relation of formal context, which indicate for each tasks which are the necessary data for its execution. As shown here, this table represents a binary relation of the formal context with 5 tasks and 5 datasets. From the formal context, we generate the Galois lattice. So it is generated by the Galicia. The Galois lattice is composed from a set of the formal concept. The seed here, the couple task data is considered as formal concept. Now, I would like to present the steps of the proposed solution, which are FCA, a agent-based workflow level distributed data placement strategy, and the second, the placement of intermediate dataset. For further understanding, let us look at the first step. Since our proposed solution is based on our previous work, it is necessary to go through its main concept briefly, that are represented in this schema. From a set of tasks and data, we generate the formal context, then we choose an algorithm for the construction of the Galois lattice related on the FCA. After this, we select the candidate concept and we affect the data in the appropriate data center or the storage service. Actually, the basic idea of our solution is to map the data to the storage service using agents. In this step, each agent is modelized by a dataset that its main objective is to select the appropriate storage service to place the data. This is based on the idea that the formal context can be partitioned on a set of sub-formal contexts. Thus, each agent is mainly responsible for construction of the formal subcontext, organizing the dataset and tasks as a set of formal concepts, placing the set of fixed dataset and their dependency, and placing the remaining flexible dataset. As a large amount of data may be generated during the workflow execution, and they need to be used as input data set of other tasks. The second step of our solution is the placement of the intermediate data set using an incremental algorithm by updating the generated Galois lattice by adding this data set. We have chosen this algorithm for the reasons below. When adding in new data to the lattice, number of the concept increases and the execution of the construction and the time of the construction and update of the lattice increases also. Then this algorithm can reduce the unnecessary computational time by avoiding rebuilding the lattice from scratch. Second, it improves to prevent unnecessary comparison between concepts by adding a new field to avoid repetitive access to the visited concept. Experimentation. We have tested our proposed solution using 4 types of scientific workflows: epigenomics in biogenetics, montage in astronomy, LEGO in network of gravitational wave detection, SPIDE in bioinformatics, and CyberShake in earthquake. We have chosen these workflows since they represent a wide range of application domains, and they have distinct structure and differ greatly in the number and size of datasets. We have used the Cloud SIEM as an extension of Cloud SIEM simulation environment. Our proposed solution was compared to the other strategy, the FCA-based approach, the genetic population-based meta-electric optimization strategy, and K-means-based clustering. Execution time, workflow communication energy, total data movement are the comparative performance analysis. We did our experimentation for 2 scenarios, the first by varying the number of workflows and fixed the percent of fixed data set, and the second varying the number of fixed data set and fixing the number of workflow. So in the first scenario, the number of workflows is variable from 2 to 5. Each workflow has tested for 100 tasks. The ratio of fixed data set among these workflows is fixed at 20%. So, result reached in these figures reveals well that our strategy reduced the execution time compared to K-means-based approach, FCA-based approach, and PDA, the genetic algorithm. Also, I would like to draw your attention to these figures. In fact, our solution has reduced the total data movement comparing to other strategy. Also, our proposed solution reveals well that our strategy reduces well the communication energy consumption. For the second scenario, we have fixed the number of workflows at 5 and varying the ratio of fixed dataset from 10 to 50%. From this figure, the comparison of total execution time while varying the ratio of fixed dataset, we can see that our proposed solution is better than the other strategy in reducing the total execution time. In the same manner, it is better in reducing the total data movement and also the communication, the energy consumed during communication between storage service in cloud computing. So, during this presentation, a novel distributed data placement approach based on a set of cooperative agents is proposed. It meets the following objectives: placement of multiple workflows based on the FCA approach and the multi-agent system, considering the fixed, flexible, and intermediate dataset. Simulation experiments indicate that our proposed solution outperforms other strategy by reducing the execution time, total data movement, and communication energy. As perspectives, we plan to treat the following consideration: explore the history of the data to predict its size. This prediction can be useful in the data placement process, and to apply our data placement solution in the context of big data application, in particular in data streaming application. Thank you for your attention.